Hey everybody, and welcome back. Today we're going to be talking about scientific notation. In this video, we'll learn how to convert between scientific notation and standard form, and then we're also going to talk about how we can use scientific notation to choose more appropriate units to represent quantities based on certain situations. So let's go ahead and get started. Let's start with what scientific notation is. Scientific notation is a format that we use to represent a very large or very small value as a product of a factor and a power of 10. One thing we have to remember is that the factor needs to be greater than or equal to 1, but less than 10. So for example, we need a value in the form of a times 10 to a power. And let's put that power as x, okay? A needs to be in between 1 and 10. It can be equal to 1. Okay, but it cannot be equal to 10. So in other words, it needs to be a single digit value. Okay? All right. Let's do a couple of problems to get more used to this. First, we're going to discuss how we write these quantities or values into scientific notation. So in this first example, we need to change 173 million into scientific notation. Our first step is to figure out what value of 173 million should we have as our first factor. Remember, this factor, we noted it to be A, needs to be greater than or equal to 1, but it has to be less than 10, okay? So in 173 millionths, we're moving our decimal so that we find A, or our factor. And turns out we need to move our decimal all the way over here in between 1 and 7. So now we have a value of 1 and 73 hundredths. Then we're going to take that 1 and 73 hundredths and we're going to multiply it by a power of 10. Now keep in mind that these two formats need to be equivalent to each other. So whatever power of 10 we multiply 173 hundredths by, whatever power of 10 we multiply 1 and 73 hundredths by needs to be equal to 173 million. These need to be equal to each other. So how would I get 1 and 73 hundredths back up to 173 million? And the answer there is we would multiply it by a greater power of 10. So we would multiply it by a positive value of 10. And then if we remember or understand our powers of 10 right, all we have to do is count how many decimal places it moved, because whenever we multiply or divide by powers of 10, our decimal will just shift over 1. So in this example, to get 1 and 73 hundredths, our decimal moved 3, 6, 7, 8 spots. So we're actually multiplying that value by a power of 8. And that is our scientific notation of 173 million. They're equivalent to each other. So if in doubt, always just double check yourself. Okay, what is 1.73 times 10 to the 8th? Well, it's 173 million. Check, I know I got it right. Let's try the next one. Here we have 32 10 millionths, And we need to express this in a scientific notation format. So once again, let's first figure out our A. It needs to be between 1 and 10. So we're going to move that decimal until we get a value that's between 1 and 10. In other words, we're going to move it right in between that 3 and 2, so we get 3 2/10. And we're going to end up representing 32 10,000,000ths as a product of 3.2 times a power of 10. Now, what is that power of 10? Okay. Again, we want these values to be equal to each other when done. So let's count how many spaces we moved our decimal. 1, 2, 3, 4, 5, 6. Okay, so it's going to be a power of 6, but which direction did that decimal move? Or which direction should our decimal move? Okay, we have, oh dear heavens, I'm trying to get that 6 looking like a 6. There it is. Okay. We have 3.2, and we need to move that decimal to the left in order for it to become 32 10,000,000ths, like it was before. In order for, when we go that direction, we're actually decreasing this number by a power of 10. We're dividing that number by a power of 10. So when you need to go left to make this factor less than what it is, we need to have that multiplied by a negative power of 10. Okay? So we need to move it back 6 spots. Therefore, we have to put it times a power of 10 to the negative exponent. Okay? Long story short here, whoops. If we have a negative exponent in scientific notation, we're looking at a smaller number than what you see. If we have a positive exponent in its scientific notation form, we're looking at a bigger value than what is written in our first factor. Okay? So that's how we convert into scientific notation. How do we convert back into standard form? And once again, it's all a matter of understanding what's going on. Okay? If I have 10 to the negative 4th power, well, we just had our lesson over negative exponents. This means 10 to the negative 4th power is the same thing as 1 over 10 to the 4th. And since that's the case, we're taking 3 22/100ths times a fraction. Well, and not just any fraction, 1 over 10 to the 4th. So that is essentially dividing. So we're essentially dividing it by a power of 10 to the power of 4. When we divide, a number decreases. So if we're dividing by 10 to the 4th, we must move this decimal left 4 spots. Because when we multiply or divide by a power of 10, the decimal just moves over 1. The trick here is figuring out which way that decimal moves. Okay? If we have a negative exponent, it's getting smaller. So we're going to move that decimal left. Okay? So this decimal is going to move left 4 spots. 1, 2, 3, 4. That's where it's going to be. And then we just plug in zeros for those locations that had no digit, like so. Okay? So there's our standard form. In the next one, we have 7 9/10 times 10 to the 5th. Well, 10 to the 5th power is the same thing as 100,000. Okay? When we're multiplying a number by a power of 10, we're moving that decimal over once. for each power of 10. So this decimal is going to move over right because we're enlarging this number. So 7 9/10 times 10 to the 5th power is the same thing as 790,000. Simply just moving that decimal over 5 spots. 1, 2, 3, 4, 5. Making sure we're going right because we are multiplying by power of 10, the positive power of 10. So we're moving right, we're increasing or enlarging this number. Let's see how this might fit into some real play action here. Okay. In modeling real life, we have a dog that has 100 female fleas. And we want to know what the total amount of blood that is being consumed by the fleas each day. And then we need to think about expressing our answer using an appropriate unit. Information we need to know is that a female flea consumes about 1.4 times 10 to the negative 5th power liters of blood each day. All right, what does that really mean? Well, let's change it into standard form. So 1.4 times 10 to the negative 5th, changing it to the standard form, and timesing it by 10 to the negative 5th, negative, meaning it's a fraction, so we're going to move left 5 spots. 1, 2, 3, 4, 5. We end up with 14 millionths. Now, to figure out how much the total amount of blood that's being consumed each day, we know how much one female flea consumes each day. That's 14 millionths liters, okay, of a liter. Well, times that by 100, which is really just 10 to the power of 2, or 10 squared. So move the decimal over twice, move the decimal back twice, and now we have 14 10,000ths. So these 100 female fleas are consuming 14 10,000ths liters blood, but that doesn't make sense still. So that's where this expressing your appropriate unit comes in. So how else might we express this instead of terms of liters? Okay, because this is still rather small for us to comprehend. And another alternative way is to recognize that, well, we can change this to milliliters. So how many milliliters is this equal to? So if we have 14 10,000ths liters, let's set that equal to milliliters. Now, how do we do that? Well, really, this is called item analysis. So this is this is altogether another topic. But in order to do that, we're going to multiply it by a unit of 1, where we compare milliliters to liters. We have to know a relationship between milliliters and liters. And for those of you who have already learned your conversions, you would know that 1,000 milliliters is equal to 1 liter. So simply just multiplying this, those liters cancel, we end up with 1.4 milliliters. And that value, it makes more sense. It flows nicer. So that is a more appropriate unit is what we say. Right? All right. So here's a couple of problems that I'd like you to try. Practice using scientific notation to represent standard form numbers, and then also using scientific notation to rewrite those numbers in standard form. So going to and from scientific notation in standard form is our goal here. Oops. And I didn't put those ones, so don't worry about number 7. So I want you to focus on just these first 6. Pause the video, try them out, and I'll be back with the answers. Now that you've tried these problems, let's go over the answers and see how you did. For number 1, writing this in scientific notation, your first value, or what we're calling your factor, should have been 6 75/100ths. Multiply that by 10 to the power of 8. Oops, there you go. This is your scientific notation form. Number 2, you should have had 8.4 times 10 to the negative 8. Number 3 was, oops, excuse me, sorry, got a little messy with that handwriting. Okay, 1.2001 times 10 to the negative 5. It's a negative there. Number 4, standard form. There you go. 6 zeros after that decimal, and then 48. Number 5, 38,760,000. And then lastly, number 6. Voila. Okay. Thank you for joining me in this video as we explored scientific notation and how to convert between scientific notation and standard form. Till next time, this is Mrs. Struble with Struble Math. Bye.